Hello 7th graders, this is Mr. Humphreys. We are in section 3.7, covering percent of change. Now you've talked about percents back in elementary school and in 6th grade. However, we're going to take what you already know with percent of change and apply it as well to something called greatest possible error and percent error. So let's start off with something you've already done. So let's suppose that you have a sweatshirt that costs $20 and the price of the sweatshirt increases by $2. You can express the increase as a percent. So let's write this down. What's the increase? It's increasing by $2. Out of what? Out of 20. That obviously equals 1/10. Now as a percent, you know that is 10%. You'll notice that I color-coded here that the red, the increase, was $2. The original price was 20. So we took the increase and we divided it by the original price. So as you can see, there was a 10% increase in the price. This right here is an example of percent of change. Now, percent of change can be represented by the ratio. Here's your important key concept today. So here's your key concept. Percent of change, there's your vocab word, is the ratio, here it is, your fraction, the amount of change divided by the original amount, expressed as a percent. Now, percent of increase, that's a vocab word, but you don't need to write this down. But increase is when the price goes up. Decrease would be when the price goes down. So the amount of change can be represented by an increase or a decrease. So we're just going to review this as a basic percent of change problem. Example 1. The price of a sweater decreased from $29.99 to $24.49. Find the percent of decrease. So if you remember our formula, we have to figure out what the percent of change is and divide it by the original amount. Well, obviously our percent of change is just going to be subtracting $24.49 from $29.99. So if we subtract, we have a decrease of $5.50 divided by our original amount of $29.99. Now if we divide that, we're going to get approximately, now remember we're going to round, approximately 1800ths or 0.18. But that's as a decimal. We have to change that to a percent. So we have a percent of decrease of approximately 18%. All right, the next thing we're going to talk about is probably new. I want you to think about the last time you measured something using a ruler. When you measured, you probably measured to the nearest inch, half inch, centimeter, millimeter, etc. Now obviously when you measure something, no measurement is going to be absolutely exact every time. So you always measure to the nearest something, to the nearest inch, to the nearest eighth of an inch, to the nearest centimeter. You never are going to get something exact, so you always go to the closest something. So this is called the greatest possible error. So here's your vocab word. The greatest possible error in a measurement is 1/2 of that measuring unit. So let's put this in an example. So example 2. You use a beam balance to find the mass of a rock sample for a science lab. You read the scale as 3 8/10 grams. What is the greatest possible error? So here's how you deal with it. The greatest possible error in measuring something is 1/2 of that measuring unit. So here's what we measured, 3.8. Since we measured to the nearest tenth, that means we measured to the nearest tenth of a gram. So that means we measured to the nearest tenth of a gram. So this right here is what we measured to. But up here in our problem it says it's 1/2 of that measuring unit. So you're going to take a half of 1/10. Well, half of 1/10 is going to be half of 0.1, and half of 0.1 is 0.05 grams. So that's the greatest possible error. So this right here is your answer, 0.05. Now I'm going to take that one step further. Now the book does not say to do this in our example, but what that means is this is going to fluctuate, the 3.8, either up 0.05 grams or down 0.05 grams. So this is the fluctuation, the error that we could have of measuring either way. Since, remember, it might not be an exact measurement. But our answer is 0.05 grams. So example number 3. You measure a room and you make a diagram, shown on the right, which I've shown you here in blue. Use the greatest possible error to find the maximum and minimum possible areas. This is where we're going to use the greatest possible error to figure out an actual example. Kind of like I just showed you in example 2. So let's first start off with what we're measuring with. Well, we measured our room as 13 feet by 7 feet. Since I measured in full feet, you have to take a half of that. So my measurement, my greatest possible error, I'm going to abbreviate, greatest possible error is half a foot. So that means both of these values here, the 13 and the 7, could be actually half a foot higher or half a foot less. So each of them could be half a foot higher or half a foot less. So we have to find the maximum and the minimum possible areas. So let's start off with the minimum. Well, the minimum obviously would be if these values were both lower. So if we take off a half a foot, so if we take 13 feet, we subtract half a foot, that means it's actually going to be 12.5 feet. Times 7 foot, subtract half a foot, that's going to give us 6.5 feet. So since we're talking about area, we have to multiply, and that gives us 81.25 squared feet. So there would be our minimum possible area. Now maximum is just the opposite. Instead of subtracting half a foot, our measurements could actually have been a half a foot higher. So we're going to add half a foot to both 13 and 7. If we multiply 13.5 times 7.5, we get 101.25 squared feet. So my maximum value is 101.25 square feet. My minimum value is 81.25 square feet. The last thing we're going to talk about is percent error. Percent error is another useful way to think of an error in measurement. It is the ratio of the greatest possible error, or the greatest possible error, and the measurement. So we're going to take the greatest possible error divided by the measurement. Example number 4. We're going to use that percent error in this problem. Suppose you measure a CD. You measure its diameter and you get 12 1/10 centimeters. 12.1 centimeters. I want you to find the percent error. This is actually used so much in real life. Like when actual measurements are given, they're always going to say there's a percent error in a problem. That's what this is. So, since the measurement here, right here, we're talking about the nearest tenth, we take half of a tenth, so half of 0.1. That gives us a greatest possible error of 0.05. So that number goes on top. And we divide it by what our actual measurement was. So our actual measurement was 12.1. If we divide, we get approximately 0.00. Let's actually make this a little better since it looks like I'm drawing at a slant. 0.0041 and a whole bunch of other numbers. That's as a decimal. So we have to multiply by 100 to give us an approximate percent. So that would be approximately 0.4%. So the percent error is about 0.4%. We are now going to put it all together in one problem. Example number 5. Let's say you are measuring a case for something, and that's what you calculated in centimeters over here on the right. I want you to find the percent error in calculating the volume. So we're going to start with what we know. Since it's a rectangular prism, you know that we use length times width times height. Step 1, find the actual volume. So you're going to take 6.8 times 1.6 times 10.9. If you did this, you would get approximately 118.6, or if you wanted to round to the nearest hundredth, 0.59 cubic centimeters. Now you're going to see why we're doing to the nearest hundredth. Because here's what's going to happen. We now have to find a minimum value and a maximum value. Now, I'm going to actually change this here. We're not going to have enough room to do max up here, and it won't let me erase it, so I'm going to put max down here. So minimum value. So how do you find the minimum value? So let's start by finding the greatest possible error. Since we look over here in our measurements are all measured to the nearest tenth. So our greatest possible error is going to be half of 0.1, which is going to be 0.05. So we're going to subtract 0.05 by each of these values. So we're going to take 6.8, subtract 0.05, and our minimum value I'm going to do in blue, so that would give us 6.75 times 1.6, we subtract 0.05, we're going to get 1.55, times the height, which is going to give us subtract 5 hundredths, and that gives us 10.85. This is why we're measuring everything to the nearest hundredth, is because up here, that's our greatest possible error. So when calculating your volume here, 6.75 times 1.55 times 10.85 is going to give you approximately 113 and 52 hundredths cubic centimeters. Now we're going to do volume in maximum. The maximum now, we take our greatest possible error and add it to each of your numbers, the original numbers. So that would be 6.85 times 1.65 times 10.95. We're going to get an approximate volume of 123.76 cubic centimeters. So here's what we have to do next. Since we're talking about volume, example 4, we didn't have to figure anything out. Here we have to find volume. You're going to take your original amount. Here it is. This is important. This is kind of confusing. Your original amount. We now have an amount that's less than that and an amount that's greater than that. You have to find the difference of either. So if I take my maximum, I'm going to start with my maximum, and I take 123.76 minus 118.59, your maximum gives you a difference of 5.17. This amount here is 5.17, or 5 hundredths, higher than the original. Now, if we subtract 118 and 59 hundredths and 113 and 52 hundredths, we're going to get 5 and 7 hundredths. So this is lower. Which one is the greater possible error? Well, it's your maximum. So your maximum is a greater possible error. So here's how you take that. Your greatest possible error is 5.17 divided by what the actual measurement was. Well, the actual measurement is going back here. That goes on bottom. We divide, and that gives us approximately 0.043, etc., which is approximately a 4% error. So when finding the volume of this, you have an approximate 4% error.